Bismillahirrahmanirrahim. Assalamu alaikum. This is lecture 9 of the Artificial Intelligence course. Problem solving agent is a goal-based agent that decides what to do by finding sequences of actions that lead to desirable states. In the last lecture, we have discussed on the definition and formulation of the problem using some toy problems. That lecture also introduced the concept of basic search algorithms for problem solving. In today's lecture, we will discuss on some of the popular classical search algorithms, mainly focusing on the uninformed search algorithms. We make decisions every single day. Some decisions are simple, others are more complex. When we are making a decision, we need to engage our problem solving and decision making skills to improve the quality of our decisions and to achieve consistently good results. Similarly, before actually doing something or to solve a problem, an intelligent agent explores possibilities in its built-in knowledge. We can say that search is mental exploration of possibilities. Search explores knowledge alternatives to arrive at the best answers. There may have several possibilities for a single problem to reach a good decision. And when we find the solution, we execute it. Search in artificial intelligence is the process of navigating from a starting state to a goal state by transitioning through intermediate state. To provide a formal description of a problem, we need to define a problem in the following terms. Start state or initial state specifies a state that from where the problem-solving process may start. State space is the set of all states reachable from the initial states. Path is a sequence of states connected by action. Goal state or goal test is a specify one or more states that would be acceptable solution to the problem. Actually, goal state is the state to which we want to reach, or we want our search algorithm should search that state. Path cost is the function assigning a numeric cost to each path, and solution is a final path from initial state to goal state. Based on the information about the problem available for the search strategy, we can classify the search algorithms into uninformed search and informed search strategies. For the uninformed search algorithms, it uses no information about the problem to guide the search and therefore may not be very efficient. They are therefore known as blind search strategies. One do not know that if the current exploration is likely to be fruitful or not, and therefore total available search space is looked for the solution. There is no clue to determine whether one non-goal state is better than any other, or whether the one non-goal state will reach to the goal state or not. Uninformed search strategies are also known as heuristic or intelligent search strategies. It uses information about the problem to guide the search, usually guesses the distance to a goal state and is therefore efficient. Uninformed search is less effective than informed searching. However, uninformed search is still important because there are many problems for which there is no additional information to consider. Uninformed search strategies are very systematic, that all they can do expand nodes using the successor function and check whether state is a goal state or not. The following uninformed search strategies will be discussed: breadth first search, uniform cost search, and depth first search. Each of these algorithms will have a problem graph containing the start node and the goal node. It must have a strategy describing the manner in which the graph will be traversed to get to the goal state. A fringe, which is a data structure used to store all the possible states that you can go from the current states. A tree that results while traversing to the goal node, and a solution plan which the sequence of nodes from start node to the goal node. Breadth first search is a search strategy in which the highest layer of a decision tree is searched completely before proceeding to the next layer. In this strategy, no viable solutions are omitted, and therefore it is guaranteed that an optimal solution is found. This strategy is often not feasible when the search space is large. The main data structure involved in the breadth first search algorithm is a queue. A queue is an abstract data structure that follows the first in, first out methodology. It is open on both ends, where one end is always used to insert data and the other is used to remove data. Take a look at the below graph. We will use the breadth first search algorithm to traverse through the graph. In our case, we will assign node A as the root node and start traversing downward and follow the steps mentioned above. As the breadth first search will search level by level, so it will first search A and will check if it is a goal state or not, if it is equivalent to a goal state or not. If it is a goal state, then the searching algorithm will stop. If it is not a goal state, then the child nodes of the A will be visited and will be queued into the fringe, which is a queue. Now the queue is not empty since there are two nodes B and C, which are the successor are the child nodes of A. Now the node B will be checked whether it is a goal state or not. If it is goal state, the algorithm will stop. If not, it will again extract its child node, which are D and E, and will put into the fringe. Now since B is visited, so it is removed from the fringe, and C in C, including D and E, are queued in queue into the fringe. Repeat these steps until the queue gets empty or reach the goal. Let us check if the breadth first search algorithm specifies the criteria, the 4 criteria of the algorithms. This is the performance measure. Breadth first search is complete. These are the, if the goal node is at depth D, it will eventually find it after expanding all the nodes before D. To find the time complexity, assume that the root of the search tree guarantees B nodes at the first level, each of which generates B more node for a total of B square. At the second level, each of these guarantees B more nodes, yielding B cube nodes at the third level, and so on. Now suppose that the solution for this problem has a path length of D, so that level will be PD. Then the maximum number of nodes expanding before finding a solution will be 1 plus B2, B3 up to BD. This is the maximum number, but the solution could be found at any point on the ith level. Not necessary that the search will go till BD. It may be somewhere in the jth level. The space complexity is the same as the time complexity because all the leaf nodes of the tree must be maintained in the memory. And breadth first search is optimal as long as the costs of all edges are equal. Students are requested to expand this graph using breadth first search. This is the solution of the graph. Thank you.